now the idea is very simple. The idea is that because these are linear functions, if you remember, you basically gave me the answer a minute back when I asked you for these linear functions, where do you get the maxima and the minima? What was your answer? At the boundaries. Very good. So all you have to figure out is, for acceptable values of x1 and x2, there will be a region, right? Because it's a two-dimensional problem. So there will be a region on the xy plane where inside that region, all points are going to be acceptable. So once we have that region, if you think about it, the optima must lie on that boundary, right? And it will become more clear as we keep going. But so as a starting point, what we should do is we should make an xy diagram, and we should plot all our constraints on that xy diagram. Okay? So I'm going to try to do this. I have to do this nicely so that we don't get crazy answers. So let's say 0.2, 0.4, 0.6, 0.81, 0.2, 0.4, 0.6, 0.81. Okay? We only have to go in this region. Right? So that takes care of two of the constraints. That x1 has to be between those two, x2 has to be. Now let's look at x1 plus x2 has to be greater than or equal to 0. That's automatically satisfied, but this must be less than or equal to 1. So if x1 plus x2 has to be less than or equal to 1, you can see that automatically tells us, so the way to plot this is to forget the fact it is less than or equal to. Just plot the equal to line. So plot x1 plus x2 equals to 1, and that obviously is this line, right? Right?
Are we assuming x2 is on the vertical axis?
Yeah, x1, x2. Okay? So now that is the equal to line. Now can you tell me which region is the constraint satisfied? The lower triangle or the upper triangle? Lower triangle, very good. And the easiest way to do this is to take any point on either side. The easiest point to take is 0, 0. If you take 0, 0, x1 plus x2 is 0, it is indeed less than 1. So that means our acceptable region is basically this lower triangle. Okay? So now we have already satisfied all the constraints for the top three constraints. So now the last constraint, two constraints left are the ones we get from the modulus and ductility index. Yeah.
Can you explain the acceptable region again? Sorry.
So now here x1 plus x2 equals to 1.
Right.
We are interested in the region where x1 plus x2 is less than or equal to 1. Right? So it's either going to be this region or this region. So you take any point. So you can take here. If you take here, you get 0 plus 0 is 0, so 0 is indeed less than, so this is right. Or you could have taken 1, 1. If you take 1, 1, you get 1 plus 1 is 2. 2 is not less than 1, and therefore that region is not acceptable. Good. So we have this region that is acceptable. Okay? Now let's do the same thing with the other two constraints. So now let's put x2 minus x1 is greater than or equal to 0. Okay? So x2 minus x1 is greater than or equal to 0. So if you think about it, this will simply mean x2 has to be equal to greater than x1. Right? So now you plot the line x2 equals to x1. And that is obviously which line is that? That's the other diagonal. Right? I couldn't have come up with a nicer numbers even had I planned this. Okay, so now can you tell me which one is the acceptable region? So it's x2 is greater than
left.
So this side upper or lower?
Left.
Upper, very good. So now, therefore, the net region is only this. Right? Make sense? Because previously it was this part. Now this further reduced, divides into two parts, so the only acceptable region is this region, the shaded region. Okay? Yeah? Okay, now you're left with the last equation, which is 3x2 plus 5x1 is less than or equal to 1. So again, to do that, let's just first plot equal to. So 3x2 plus 5x1, let's just plot equals to 1. Okay? Alright, so to plot it, I mean, you all know how to plot it. The easiest way to do this is to, let's just first find what happens if x1 equals to 0. If x1 equals to 0, x2 is 1/3, right? So 1/3 is 0.33. So 0.2, 0.3, 0.33. This is 1 point on the line. If x2 is 0, x1 is 0.2. So this is this line. Right?
Yeah.
Okay, I'm sorry. This line. Okay? So now of course the question is, what is the acceptable region? Is it below or above? I'm going to give you a second or minute to think about it. Don't give an answer. I want everybody to think about it. So what we are interested in is less than or equal to 1. Okay, is it the lower or upper?
Lower.
Lower, very good, the triangle, right? Okay, so let's just shade this. Okay, so now we are done.
You shade it too much.
Oh, okay, I'm sorry. Excellent. So now we need to, so this point is obvious, we know this. This point is, we know this. Now we need to figure out what this point is, right, at which this line intersects that line. How are we going to do that?
Make them equal to each other.
Right, exactly. Let's make them equal to. So this line is x1 actually equals to x2. This line is 3x2 plus, so if you make x1 equals to x2, you get 3 plus 2, 8. So 1/8, right? Both of them are 1/8 and 1/8. Right? Yeah? So 1/8, well, let's just call it 1/8. So this point is 1/8, 1/8. This point is, of course, 0, 0. And this point is 0, 1/3, right? Great. So this is what is called the region of interest or acceptable region. So every point within this triangle satisfies all our constraints. Does it make sense to everybody? All right. So now how are we going to figure out where does f become a minimum? So we are interested in f becoming a minimum, right? So of course the question is, why do we make a statement that this has to be achieve an optimum at the boundary though, right? So because everything is monotonic, right? But you can actually, I can give you a little bit, I can actually do a little bit better than that. So let's draw lines of constant f. So now, so that function, so I think when we were doing Lagrange constraint optimization, I explained to you how we can draw all the constraints and then we can draw level curves of constant f, right? So let's do that. So let's start with f equals to 400, 300, 200, and we'll draw all those different curves. What can you say about those curves? For different values of f, they will all be lines, right? What can you say about those lines? They will all be? Not that, not right answer.
Sorry.
Unless somebody speaks that language. They will all be parallel, right? All right, so let's plot first f equals to 400. So that would be, if f equals to 400, you have 3x1 plus 2x2 equals to 0. Right? Let me see if I have a colored, yeah, I do have colored chalk, so I'm going to draw these curves in color. Right? Does everybody see why that's equal to 0? because you put 400, 440 cancels, you can don't have to go to minus sign, you divide by 100, you get 3x1 plus 2x2, right? All right, so let's draw that line. So again, as always, the best way to do this is to choose x1 is 0. So if x1 is 0, of course, x2 is also 0. So this line starts at 0, 0. And then let's figure out what happens at x1 equals to 1. If x1 is 1, of course, the value is negative. But how negative? If x1 is x1 is 1, you have x2 equals to minus 3 divided by 2, right? Right? Okay, so minus 3 over 2 is minus 1.5. So basically it will be off the board. So you can see this line will basically go like this. Something like this, right? So this is the line where f equals to 400. Okay? All right. Now what if f is not 400, but let's say f is 300. So now so that was f equal to 400. Let's plot a line f equals to 300.
We'll do another color.
Sorry?
Do another color.
What'd you say?
Another color.
Okay. I do that. Blue. And that's not, what is this color?
Blue.
Indigo.
Indigo, yes. Not blue, it's indigo.
Fancy, fancy.
What?